All right, let's begin. So most of you should have received your homework 2 grades by now. And if you haven't, there's probably some issue with your code. Lena has posted, she has a post on Piazza explaining what you need to do to make sure that we can grade your assignment. You will lose points because it didn't conform to the specifications we put in. I think maybe even lab 2, 3 grades are out, and we'll be getting those soon. The midterm will be graded hopefully by the beginning of next week. So wait for that. About homework 4, there are 2 versions. There's the main version, the alternate version. The alternate version does not give you as many points. If you do both of them, then you have a chance of recovering some of the points you lost in homework 1 or homework 2. Like it's a bit of a complicated rule. Look at it, and it should hopefully be clear. What I thought I would do, actually any questions about homework? Okay, yes? Sorry, there's a typo. I thought I fixed that, so look at the latest version. Yeah. Yes? Sorry? Can you only recover points from homework 1 and 2? No, not 3, no. So I actually thought I would explain a little bit about the logic behind homework 4 and how to solve it, if that would help. Okay. So how many people are like completely stuck? Okay, all right. So it is a bit tricky. In the end, the code is not going to be that long. So this is not like homework 2 or 3 where you have to write lots of code, but the logic is relatively straightforward. It's the opposite. The logic is a little tricky, but once you figure out the logic, your actual code should not be too long. So interestingly, this is less 12B and more of artificial intelligence or game theory. But understanding 2-player games, that's really what homework 4 is about at some level. So right, you have your chessboard, and you have 2 players, white and black. So white plays, then black plays, white plays, black plays, so on and so forth, right? And you start off with some setting of pieces, and you have to see, let's say, can W win in, let's say, 3 moves? Okay, so can W win in 1 move? That shouldn't be too hard to do. Most of you see that? So it's not hard to get 14 points on this assignment. Can W win in 1 move? The only thing you need to figure out is how do you find all possible moves for W? And that I'm not going to tell you. But if you think about it, W has a bunch of possible moves. So W has some set of possible moves. If this is a queen, then the queen can move in a bunch of directions. If this is a rook, then that can move somewhere. And of course, it depends on the other pieces, what's getting blocked. But that's basically been solved in assignment 3, like checking if a move is valid. So W has some set of possible moves. You need to generate all of them. And when I say all possible valid moves, okay, you need to generate all of them. This I won't tell you how to do. But if you can figure this out, then you would get 14 points. But now, so now what happens? So think of the best way to represent what's going to happen in 3 moves is something called a game tree. Now, you don't actually have to code up the game tree. This is only a way to help you think about how to solve the problem. Again, you don't need to actually code up the game tree, but it's a way of thinking about it. So the way to think about it is basically, you have the starting board here. This is the starting board. So W plays first. So W has a bunch of moves that she can make, right? Each of those, so this is W, results in a new board. Does that make sense? Each move of W results in a new board. Now, depending on what that board is, black now has some options. Those options are different depending on W's move, right? So this and this are potentially different. Does that make sense? Depending on what white moves, then black has some set of options. Of course, each of these now results in some board here. And finally, W plays again, and that results in some set of boards. Does this make sense? So this is called the game tree. Now, you don't have to build all of this. But just for a thought experiment, imagine you wrote out this entire game tree. Just think of writing it down on paper. Then can you figure out if W can force a checkmate? So what happens is, if you look at any of these resulting boards at this level, so this is, you can call this like level 1, this is level 2, and this is level 3. And for simplicity, suppose if this was already checkmate, then assume that nobody makes a move. Right? There's no possible move. So next level is just the same. So you can look at these boards, and you could imagine going through each of those boards and marking out whether it's a checkmate or not for W. Right? So you could say, yeah, that's checkmate. I mean, W wins here, W wins here, W wins here, W wins here, but not in the others. Does that make sense? Now, suppose you actually wrote out this entire game tree for 3 steps, and you figured out which of these actually result in checkmates. Can you now figure out whether W can win? Yes. Yes. Yeah, so can W win in 3 moves? So white makes 1 move, black makes 1 move, white makes 1 move, and then white wins. Right? So that's what I mean by X number of moves. I don't mean X number of moves for white. Yeah? Sorry. So my question is, if you actually wrote out the entire game tree, can you then figure out whether W can win? How many people are not convinced? Don't see it yet. Raise your hand. So everyone sees that? And so how do you find a winning move? How do you find a winning move? Yes? You guys see it? So you raised your hand first. Yeah? Sorry? You have to be careful, right? So let's say you built this game tree. This move that W makes does not result in a checkmate. Maybe none of these moves result in a checkmate in the very first go. So you have to be a little careful. How do you know which of those moves is a winning move? Because it's 3 moves down that something's going to happen. Yeah? You have to trace the tree back up, yes, but how? I mean, so this is where you have to, this is the logic that we need to figure out. How do you figure out which of these, if any, is a winning move for W given the game tree? So think about, yes? Yes, you have to search for it, but how do you search for it? That's the question. So think about it. What does a winning move mean? A winning move for W means no matter what black does, white has an answer. Let me write that down. A winning move for W is W makes a move, then no matter what black moves, W can force checkmate. Does the English make sense? Right? That's what it means, right? So I make a move, and then no matter what black moves, white can force a checkmate. So everyone seemed fairly convinced that given the game tree, they could figure out what a winning move is, but I still don't see, I still don't hear an answer. Yes?
So it would be similar to homework 1 where you would use recursion and
Mm-hmm.
you go through each of the instances, and then when you hit level 3, if it returns as like false, it's not in checkmate, then like I guess use recursion to go back up the tree and then just mark it off, I guess, whatever the checkmate is on.
Good, okay, so you're getting there. So you need to use recursion, clearly. Recursion is the way to do it, because the tree obviously has a recursive structure. But there's an asymmetry between white and black, right? You're trying to force white is trying to make a win, and black is trying to prevent white from winning. When you do a recursive process, you're just running the same code over and over again. So obviously, the logic that white is using is not the logic for black. There's a difference between. This is actually very interesting. So this comes up in, you wouldn't think, but in counterterrorism. In counterterrorism. In research on counterterrorism, you think of, I don't know, there's like the police or the protection force, and there's the terrorists, and it basically builds up a game tree. You say for every action that the protective force has, the terrorist has a potential response, and you want to make sure the protective force has a response to that. So for example, in deciding which flight should you put air marshals on, obviously there aren't enough air marshals to put on every single flight and from every place. And so, I mean, there are people in the government, actually analysts, who decide where you should put air marshals, and they actually use logic like this. You kind of think, which are the flights that are most potentially likely to be attacked, and you put air marshals on those. Right? So you have to change your strategy depending on what the other player is doing. And it's something that happens over here. W makes a move, and then no matter what black moves, W can force a checkmate. So what is the logic for finding such a winning move? Does the question make sense? Yeah? What does that mean? So what does a winning move mean? Maybe that's the question I'm like. That's what I'm trying to get at. What does it mean for W to be able to win in a single move? Yeah. He puts black in checkmate, not in the first move. So that's the thing, right? So W can win in 3 moves. That does not mean that W puts black in checkmate in the first move. Sorry, there's a hand that went up in the back. Yes? You can do weak or strong. I mean, I think weak gives you less points and strong gives you more. But then you already have the code for doing strong checkmate in homework 3, like in our solution. Yeah? So in the game tree, obviously you're keeping track of all the moves. I mean, think of actually playing, I mean, I don't know, maybe you guys don't like chess, but maybe you play checkers or something, or I don't know, what not poker, because that's not a good example of a 2-player game. I don't know, tennis, like who plays tennis? Right? Yeah, okay, so don't you think like, okay, do I try to go for the person's forehand or backhand, and if I do that, then what will they do and how will I respond? Or do you guys not think? Do you guys just hit the ball as hard as you can and hope for the best? Huh? Right? So you do strategize, right? When you're playing any game, any sport, you strategize because you kind of think, okay, if I do this, then the opponent will do something and I need to have a response for that. Yeah? No, so it is not necessarily the case that the first move has to be check. Why? Maybe it's a sacrifice. Maybe the very first move is a sacrifice. How are you going to figure out? Yeah? Three moves or less, but yeah, let's not get it. Yeah. Yeah.
So it's a winning move for white if there is some level 1 move that it can do, where for every level 2 black move, there is at least one checkmate possibility.
Did everyone hear that? So there is a winning move, and I'll go over this again. So let's say this is a winning move if, for every option that black has, white has some option to force a checkmate. It doesn't have to be the case that all of white's options have to be checkmate. But as long as there's one, and there has to be one for each move over here. Does that make sense? Yes? There could be multiple solutions. Don't worry, we will check through all of that. Yeah?
So you're saying black has to be trying to avoid checkmate.
Exactly. And black has no way of avoiding checkmate. That's what a winning move is. So that's why I said there's an asymmetry between white and black. White is trying to force checkmate, black is trying to avoid checkmate. Right? So the logic is different. You have to have slightly different pieces of code for what white is doing and for what black is doing. So again, does this picture make sense? So what this means is white makes a move. Such that for every possible, next move that black makes, white has a move that results in checkmate. White makes a move such that for every possible next move that black makes, white has a move that results in checkmate. If this is true, then white can win in 3 moves. If this is not true, just a second. If this is not true, does that mean that black can win in 3 moves? It only means that white cannot win in 3 moves. So black can avoid checkmate in 3 moves. Right? So there's an asymmetry between white and black. You got a question? Mm-hmm. No, you need to be able to, you need to show that for any move that black makes, white has a response. Because if there is a move so that white has no response, then of course black can avoid checkmate. First, you had a question, and then that answers. Okay, yeah. Yes. How would it work for 2 moves? Let's get to that later. Let's first figure this out. I'm not convinced that you get it, so so you need to ask more questions, because I'm not sure what is the part that you don't get. It's funny, you might think that you can gauge. I don't know, I can just feel it in the air. Like when you guys don't get it, I don't know what you project, but the atmosphere is like, I don't get it. Okay? So in the back, yes. Yes? Sorry, say that again? No. No, so remember, suppose black had a move over here such that there was no checkmate. Right? Well then, if white made that move, black would simply make this move, and white wouldn't win. Sure, I mean, you're saying that black could be stupid and white could win. That's true. But you have to be able to argue against a black who's smart. When I say, can white win in 3 moves, maybe I didn't think that I'd have to clarify this, but I will. When black is smart. Not when black is dumb. When black is dumb, yes. Black could just open up all the pieces and sort of make sure that the king can be attacked, but no. You need to do it when black is smart. Yeah? No matter what black does. Exactly. Yes? Yes, black will choose the best move every single time. I mean, isn't that what you do when you play a game? Don't you choose the best move for you? Or do you like no, I want to be nice to the other guy? So in this case, white wins when black chooses the best possible move at every stage. Right? That's what it means for white to be able to win. Yes?
Would you recommend then finding all possible moves for black after white wins?
Exactly. Good. Good point. So how are you going to code this up logically? For every move that white makes, you then have to find all the possible moves for black and make sure there is a response to each of them. Right? Good. So, and that you will do using recursion will help you do this process. Recursion will help you figure out all these moves, because the process for finding out these is the same as the process for finding out these and these. It's recursive. Yes? So that's a good question. How long do you think this code would run? I don't think it'll be that long because essentially I'm not going to ask you win in 10 moves. Because if you coded that up, then you shouldn't be in this course. You really need to be working somewhere in the AI industry. So, because in some sense, that's what, I don't know, you guys have heard of Deep Blue? So what Deep Blue does is, what made Deep Blue beat Kasparov was that Deep Blue could think many more levels than any previous computer program. And the way it does that is actually by not building out the entire game tree, but ignoring various portions based on its knowledge of chess. So it says, this is a stupid move, I'm not even going to look at that. And how does it figure out it's a stupid move? Well, there's a lot of analysis. They actually have chess grandmasters give it advice on what is the right algorithm for that. Someone had a question? Yes? Oh, there and there.
Can I use a stack to replace recursion?
Good question. Can you use a stack to replace recursion? You can. So a stack is a very convenient way to represent all the moves. Every time you generate all possible moves, you push them onto a stack, and then you kind of pop them to go through all the examples. You can most certainly use a stack. Yes? Maybe. I mean, in this case, you're not going to have more than 3 levels of recursive calls. Again, the maximum, I'm only going to ask you win in 3, maybe 4 moves at most. I'm not going to ask you anything more than that, because then it becomes too expensive. There actually aren't too many options. At every stage, you might have about 100 options. Right? So maybe you have 100 here. Maybe you'd have 100 here, and maybe 100 here. And that's a total of 100 to the power 3 options overall. And that's a million, which your code can, which you can do, you should be able to do in seconds. Yeah?
So how does even numbers of moves work? Because if you're doing white, black, white, three, if you're doing even number, would it be white, black, white, black? So like, what would that entail?
So an even number of moves, it's actually, so if it was even number of moves, then I would say, can black win in 2 moves when white starts? So white plays, and no matter what white plays, black has a response. Right? So when I say if I were to say, can black win in 2 moves, obviously I mean white has to start. White starts, and no matter what white plays, black has a response that forces checkmate. Yeah? Does that make sense? Yes?
So the 1 move and the 3 moves are white winning, and the 2 and 4 moves are black winning?
Yeah, so usually, if I remember correctly, I'll go and check again. I think I specify which player has to win. Did I or do I not? I'll go and look at it, but it should be clear from the assignment description. Yes? So black can never go into check according to the rules of chess, right? So, I mean, you can never make a move and lose. Yes?
And you're saying when black wins in 2 moves, that means white makes an intelligent move on the first move, and black finds a way to checkmate that.
Exactly.
You can find an intelligent move for white on the first move.
So if you think of the game tree, okay, so maybe let me. Okay, so let me answer this question. First, let's make sure that you understand the 3 move. Everyone understands the 3 move thing, and then we'll go to the 2 move version. Yeah, is that clear? If nothing else, maybe you'll become better game players after this, just so that it helps you think more logically about it. Yeah? Questions? Okay. Oops. Okay, so now we can say, can black win in 2 moves? White starts. So here is the starting board. This is white, which has a bunch of options. And now here is black. And so what you need is, I mean, this means, I'll just say checkmate. White is in checkmate. White loses. So no matter what white moves over here, black is able to force a win. Does that make sense? Yes? Does that mean you're looking for checkmate patterns? What do you mean? Yes. You don't have to, okay, so you don't have to get fancy on chess actually for this. You only have to understand the game tree. Because you already have code from homework 3 that decides if a particular board is a checkmate. You also have code that decides if a move is valid. So once you can list out all the moves, you just need to enumerate this logic using stacks or recursion. Note that you don't need to figure out what a smart move for white is. All you need to do is to just say for every possible move, black has a move that forces checkmate. Does that make sense? I want to make sure that's clear. You don't have to figure out chess. You don't have to be clever about it. That's actually the most interesting thing about AI. Like, AI algorithms are not smart. They're actually dumb. They just go over all possibilities, which human beings cannot. Yeah?
When you take into consideration that white starts, but white make a move that put black in strong checkmate, and then black just cannot.
So if white has a move that makes black go into checkmate, then black cannot win in 2 moves. Right? So the question of can black win in 2 moves, again, assuming white is smart. Or rather, assuming nothing about white. White can do anything. Yeah? Right. You don't print, you only will say, can black win or not. You say yes or no, or you just print a starting move. Yeah, so we're not going to ask you to actually produce such a move. Not yet, but maybe I should. Just to help you debug, I mean. Yeah? Yes, for every single move of white, black needs to have some move that forces a checkmate. It doesn't have to be all, just one. Right? Just think of it, right? You're playing against someone, and no matter what they have, you have a response that will make you win. Yes? Yeah, so I should probably clarify on that. I think you just say yes or no. I'll fix the assignment to clarify that. I'll fix the assignment to clarify that. And I think if the answer is no, then you give a move for white. I'll clarify that. For white, you give the first move, right? So in this case, your output is simply what is the first move. There may be multiple possibilities. Probably not, but there may be. But you just have to give one move. And we will verify whether that move is actually a... If it helps you think about things more, you might want to think about how we're actually going to verify your solution. And it's actually just using the same logic. Question in the back. I'm sorry? Yes? For 4? No, I mean, there's some input-output format, right? And that's what you need to follow. Do you have examples? Yeah, well, I gave you a website of examples, and I will maybe produce more that your code can run. Yeah, I can do that. The link doesn't work? Okay, all right, I'll check. Google. If you look for mate in 1 puzzles, there's a website. Surprise, it didn't work. Maybe there's some special character that actually didn't get printed out. I'll check that. Thanks. Thanks for pointing out. Questions? Does it help? Do you think you can solve it or some part of it now? Probably, maybe, somewhat. Yeah? What do I recommend, recursion or stack? I don't know, whatever is easier for you to think. Maybe recursion, just to make the code easier. Any other questions? Of course, you can always do the alternate version, which is much easier, which is just priority queues. It's just coding up a priority queue. All right, so let's stop here. Let's actually take a 2-minute break. And when we come back, I'll talk about sorting. Okay, let's resume. Let's resume with a new, or let's go back to sorting. And again, this is to some extent like 101 light. That we discussed sorting, right? Where you're given a bunch of numbers and you have to put them in order. Simple problem. And so the first algorithm we discussed for sorting was you find the minimum element, you swap it with the first, gives you that. Then you find the minimum in what's left, you swap that with the second, so on and so forth. Right? So you find the minimum, make it the first, and whatever is left, you find the minimum, make that the second, so on and so forth. And that was called what? Selection sort. Yes. Selection sort. It said for I in 0 to n minus 1, where n is the length of the array, find the ith minimum in the array, place that in the ith position of the output, and we had a piece of code. Just walk through this again. For I going from 0 to n minus 1, you first assume that the min is the ith, like the index of the minimum is just I, and then you go for j going from I to n minus 1, and try to find what is the minimum in the elements from index I to n minus 1. So you go through all j and you say if aj is less than a of min, you reset min, you swap ai and a min, and that's the code. Right? That was selection sort. So again, you have two for loops, two nested for loops. One loop is here, and in this loop, you're basically trying to find the ith minimum of the array, and then the swapping step is just sort of putting it in the right position. So that was selection sort. And we also discussed another algorithm that we called insertion sort. So insertion sort has a different logic. It says, suppose all of this is sorted, the first I elements are sorted, then you take the next element and you insert it into here, and then you kind of keep proceeding in that way. And insertion sort gives you another algorithm. So does everyone understand what insertion sort and selection sort are? Mostly. So what's interesting about both insertion sort and selection sort, so let me actually give you the code for that as well. In insertion sort, you also essentially have two nested loops, right? So you say for I going from 0 to n minus 2, you set j is equal to I, and then you do this sort of swap. Right? So you say while aj plus 1 is less than aj, you keep swapping. Right? While aj plus 1 is actually, when aj plus 1 is less than aj, then they can't be sorted, so you keep swapping, and you repeatedly do that until the whole array is sorted. So just to, I think it might be useful if I actually show you a visualization of both of the sorting algorithms. So let me get that up. Okay, so this is actually it's a nice website from San Francisco University that I use to show algorithms. So here's basically an array of numbers. And so what we can do is we can actually run selection sort and just sort of see how it proceeds. So what it does is it basically, so it starts by comparing it says min, initially it assumes min to be 14, like the first thing. And then it keeps comparing until it finds 1 is the minimum, and it keeps walking through the array comparing with 1. Does that make sense? It's walking through the array and trying to find out what the min is. So it's going to go through, of course, nothing else is smaller than 1. Let's speed it up a bit. Okay, so at this point, it's gone through the array. It knows that 1 is the minimum. And it's going to swap 1. Can you guys see the numbers? Maybe I'll just... Yeah, is that better? And so it's going to swap 1 with 14, right? And now it's going to walk through and try to find something that's the minimum. Nothing is larger than 10, except at that point it reaches 6. And then it's going to find 4, which is the second minimum. And then it swaps 4 with 10. Now it finds a third minimum. Let me just slow this down a bit. And it's going to eventually reach 6. Right? So it's coloring this. Note that it also finds another 6 over here, but it'll keep this one. Keeps the first one that it finds. Okay? And then it's going to swap 6 with 14, and it's going to proceed in this way. Sort of makes sense what's going on? That's selection sort. So you see that there's a double for loop, right? There's one loop that goes through the entire thing to find a minimum, and then that loop is repeated over and over again. So let's actually see insertion sort in action, which is very different. So insertion sort is, let's keep this here. And what insertion sort is first going to do is actually just going to swap these two. And then it's going to say 10 and 14 is sorted, and then it's going to insert 1 into that list, then insert 41, then insert 37, so on and so forth. Right? It's going to keep moving until 1 goes to the right place. Now it moves 16. 16 is going to get to the right place. Then 12 is going to move into the right place. And then 18 is going to sort of slowly walk and move into the right place. And so let me just pause that there. So at this point, observe that everything from here to here is sorted. Do you guys see that it's sort of faster? Like it doesn't keep moving this entire path through the array. It sort of builds up something. It builds up something that's sorted as it moves along. And it's going to do that. And then 90 is going to move to its place, so on and so forth. It's a very different algorithm. Question? Sorry, say that again? It's a good question. So when smaller numbers at the end, then the smaller numbers have to move all the way, and it becomes slow. So think about what if the array was decreasing, then insertion sort is effectively just going to sort of take everything and move it all the way back to its position. So it is going to be sort of slow. But so is selection sort. So it's sort of no worse than selection sort. Right? So hopefully this sort of visualization gives you a sense of what's going on. The most important thing to note here is that, right, so in this case you have this problem, right? 19 is going to sort of move all the way down to where it has to be. Is that this also has two nested loops. There's one loop that is essentially trying to insert the next element, and then there's another loop that actually does the insertion. Any questions on its, yes? I would think that insertion sort probably is, I mean, you sort of sort some part of it, and then you bring the next one, you put it in. Well, I don't know. I guess depends on what kind of a human being you are. I do merge sort, but anyway. Questions? Okay, so hopefully this was useful in sort of seeing the difference between these two algorithms. So what's important for us to discuss here is both insertion sort and selection sort use, well, say, two nested loops. And if you remember, we said selection sort makes n times n plus 1 over 2, which is approximately n squared over 2 comparisons on an array of length n. Insertion sort makes, well, it's actually less than equal to, basically the same comparisons on an array of length n. Now, if you're a little careful, you can decrease this a little bit. You can make this n squared minus n, or you can make it n squared minus 2n or something. But the point is that it's dominated by n squared. And remember, as we discussed, if n was equal to 10 to the 6, that's 1 million, then this takes forever. Or maybe not forever, but it takes like a week or something, or maybe more, maybe a few weeks on a computer. Yeah? So this is actually, this segues into what's called the analysis of algorithms. How to compare two different algorithms for the same problem. This is extremely, extremely important. And this happens over and over again, either in research or academia or industry. Because for the same problem, like sorting, you have many different algorithms, and you need to pick which one to use. So you need to have some sense of how do you compare them. So how do you compare two algorithms for sorting? Yeah? How many comparisons it makes. So, but for which input? So the number of comparisons that insertion sort makes depends on the input, right? So you could compare two algorithms. So we can compare algorithms by counting the number of operations they make. They make on an input. So I have to clarify what I mean by on an input, but does this sort of make sense? So for example, you could look at insertion sort, you could look at selection sort, and you can say, what's an operation? Well, a comparison is an operation, increasing an index is an operation, swapping is an operation, and you sort of go and you count how many operations are made for an array of size n. Yes? And we only looked at comparisons, but that's, it turns out to be good enough in this case. And you can do the same for selection sort. So I give you a piece of code, you can go and look at, let's say, insertion sort and say, how many comparisons does it make? Just to check if you're awake, or at least, or if you remember what we discussed last time, suppose A is sorted. Then insertion sort makes at most n comparisons between n and n squared divided by 4 comparisons, or more than n squared over 4 comparisons. Suppose A is sorted. Then insertion sort makes less than n comparisons between n and n squared divided by 4, or n squared divided by 4 comparisons. Think about what insertion sort was doing. Yes? No? Okay, answers? Right? So why is it that? Yes?
Because it only has to pass through the array once. It never has to swap anything. So it just needs to check each number and say, oh, this is in the right place, and just continues through the whole array.
Exactly. So insertion sort is never going to do a swap. Right? And it's actually, neither insertion sort nor selection sort are going to do swaps. But if you think about it, what insertion sort is going to do is, where's the code for insertion sort? Well, let me show you the picture. What it does is this part is sorted, and then it has to insert this. Well, it compares this with this and says, oh, this part is already sorted. Then it moves to the next one, compares that with the previous one, says, oh, that's sorted, so on and so forth. So it makes just one pass over the entire array. Right? But what about selection sort? What if I ask you the same question for selection sort? How many comparisons does selection sort make? You can talk to each other if that helps you. Yes? How much? Right. It would be yellow. more than n squared over 4. It's actually n squared over 2. Even if A is sorted. Now, why is that? Remember, we said if you have selection sort, in every pass, j goes from I to n minus 1. So it makes an entire pass through the array to find the minimum. And we said that the total number of comparisons made is a summation of n minus I as I goes from 0 to n minus 1, which is about n squared. Right? And if A is, instead of sorted, if I said decreasing, then what happens? So if A is decreasing, then what does insertion sort do? I'm going to draw myself a table over here. Answers. Suppose A is decreasing, then what does insertion sort do? How many? That's right. It makes n squared over 4. Or actually, it makes more than n squared over 4. It makes n squared over 2. Right? Because it has to go through everything. So when it's sorted, insertion sort, let's just say the number of comparisons, this is like less than n. Or it's, let's just say, approximately n. And this is approximately n squared over 4. When it's decreasing, it's n squared over 2. My apologies. N squared over 2. And this is still n squared over 2. What if it was random? What if the array was random array? I mean, to get a full solution, you need to know some probability theory, but you can kind of guess. What about selection sort? Suppose the array was random. How many comparisons does selection sort make? It's always the same, right? So it's always this. Do you expect, if things are random, for insertion sort to be better or worse? Or better? Do you think it's closer to n or closer to n squared over 2? Closer to n squared, because it actually has to move everything to the right position, right? And so, it's sort of approximately n squared over 4. It does better. Sort of, it moves like half the distance. It's less than that. The point is, looking at this, it's quite clear that insertion sort is a better algorithm, right? Is better, but not in the worst case. In the worst case, they actually are the same, or the number of comparisons they make is the same. Yes? It's a good question. Is the worst case the same for every sorting algorithm? No. No. You could have a sorting algorithm that first checks if it's decreasing and flips everything around. Right? You could just put a linear time, you could put one loop in the beginning that just checks if it's decreasing. And for that, clearly, this is not the worst case. So you can play tricks like that. Even in general, I think there may be some, firstly, there are algorithms that do way better than this. And for them, actually, that might not be the problem, like the reverse example. So what we often do in the analysis of algorithms is something called worst case analysis. You say for a sorting algorithm, you define a function t of n. T of n is the maximum number. Let's for now stick to comparisons, but in general it's operations. The maximum number of comparisons or operations on an input of size n. This makes sense? This is worst case. Because you're saying you want to really understand what is the worst that this can possibly perform. You can also do average case analysis, where instead of maximum, you would say on the average. So in average case, you would say Tn is the average number of I'm not going to define this formally because it requires more language, more probability theory language, which we don't have to get into. Worst case analysis is the most common thing. You rarely do best case analysis because you never know what your algorithm has to face. So for a sorting algorithm, you can say T of n. So T of n is a function, right? And you can imagine plotting T of n. So if you plot T of n for insertion sort or selection sort, you see something like this. So this is n, and this is T of n, and this is something like n squared over 2. Right? So what does this mean? One way of thinking about it is if you double the size, then how much does the runtime go up? If you double the size of the array, okay. Question. If you double the size of the array, that's n, how much? So let's call this the worst case running time. How much does T of n increase by? Does it increase by 2? A factor of 2. By factor. Maybe I'll say factor of 2. Factor of 4 or more. If I double the size of the array, how much does T of n increase by? Does it increase by a factor of 2? Does it increase by a factor of 4? Or more? Algebra, right? Okay, guys, you need to be able to answer this. I mean, those of you who have it, like, put it down. But the rest of you, this is algebra. I doubled the size of n. How much does T of n increase by? Yes? Doesn't it matter what n is? Does it matter what n is? No. Is it a case where maybe 2 of them are correct? Or one of them is correct and the other is not? No. T of n is equal to n squared divided by 2. T of 2n is equal to 2n squared divided by 2, which is 4n squared divided by 2. I will ask this question in the final, and if you don't get it, I'll be very angry. Right? So if you double the size of the array, the worst case runtime actually increases by a factor of 4. So does this make sense? And the way this is formally specified is something called big O notation. Now, to formally describe what big O notation means, we have to do some calculus, which I'm not going to do. But you may have heard of this. We say T of n is called O of n squared. Or it says, or you would say that insertion or selection sort are what are called O of n square algorithms. Now, what does the O really mean? Again, you need calculus to it, but basically think of it, you take T of n, and you kind of ignore any constant. You ignore the divided by 2. If you have n squared over 2 plus 5n, you say, I'm just going to ignore these little, I'm just going to ignore the smaller stuff and just call this O of n squared. Because what I'm trying to get at is really this point. If I double the size of the array, how much does it increase by? A factor of 4. So whether it's n squared divided by 2 or n squared or even 10n squared, this statement is still true. Right? Regardless of what T of n is. If T of n is this, T of n is this, or T of n is this. If you double the size of the array, the runtime goes up by a factor of 4. Yeah?
If you have like plus n cubed, then would it change?
It's a good question. So if you have plus n cubed, then what happens? Yeah, so then n cubed starts dominating. Right? So when you do big O analysis, you're basically, this is also referred to as big O. I don't want to get into too much detail about this, but we're supposed to introduce this right now so that next time we tell you, you actually understand it. So big O is supposed to say, in your running time, what is the most dominating factor? So what is the most dominating term? And so if you had something like T of n was n squared plus n cubed, then eventually this starts dominating. And so you would actually write this as O of n cubed. So, and you kind of ignore the n squared part. Again, the formal language for this requires like limits and some calculus. But one way to think about this is you're trying to say if you double the size of the array, how much does it increase by? The ideal you want is a factor 2. And I say, look, you double the size of the array, well, the running time should go up by a factor of 2. Obviously, it has to go up, because you have to read something that's larger. It would be nice if it's a factor of 2, but unfortunately, it's a factor of 4, which is actually what makes insertion sort and selection sort infeasible in practice. Does this make sense? And the O of n squared, another way of thinking about it, O of n squared means 2 nested loops. So when you have something that says 4i going from 0 to n, and maybe 4j going from 0 to I, or from 0 to n, or from I to n, one of these, and then there's something over here, this is an O of n squared algorithm. So selection sort, insertion sort, also something called bubble sort fall into this category. They're all O of n squared. Yes? Questions? And so, especially for a problem as important as sorting, remember, I'm talking about worst case runtime. One of the questions that comes up is, can you go better than n squared? Can you actually beat this? And this is actually a fairly complex mathematical question. And it was answered, I think it's in the 60s, that there are algorithms called merge sort and something known as quick sort, and also something called heap sort. We won't go through all of those, but these algorithms are better than O of n squared. How many people have seen merge sort or quick sort? So most of you have. But I will go through, I'll go through merge sort. So merge sort, quick sort, and something called heap sort are better than O of n squared. So if you actually think of plotting n versus t of n, and you plot this, maybe this is insertion sort, then merge sort looks kind of like this. Merge sort looks like that. Actually, one of the 101 assignments, it's actually something I did as an undergrad, and I think it's a really useful thing, is to actually go and plot these curves for various different sorting algorithms, and then you actually see the difference. So how does merge sort work? So any questions? Merge sort is a really weird algorithm. At least the first time I saw it, it blew my mind that something like that could even work. And merge sort is a classic case of recursion. So what merge sort does is the following. It says recursively sort the left half, recursively sort the right half. And now merge the sorted arrays to get the output. So you recursively sort this, and you recursively sort that. And then you have to put together two sorted arrays to get the input. Yeah? Heap sort? Oh, by that time I was convinced. No, merge sort is actually much stranger than heap sort, I feel. Because when you look at this, you're like, what do you mean you recursively sort? I mean, how is this actually even going to work? So let's say I have two arrays that are sorted. 100, 9, 20, 21, and 50. These are two sorted arrays. And I want to merge them to get one sorted array. Right? So I want to merge them to get my 8 elements. 7, 8. How do I do this? So what's the first element in this? 1. How do you know it's 1? I mean, okay, you can say I looked at the numbers and it's obvious that it's 1. But how would you write code to do that? Yes?
Because 1 is less than 9
Right. So 1 is the minimum of the first elements. So you compare these two. You put 1 down here. And now you move this index to that. And then you compare these two. And you say, then you put down 5. And then you move that index. And now you compare these two. You put a 9. And you move that index. And you compare these two things, you put 20, and you move that. You compare these two, 21, you move that. You compare these two, now you put 42, you move that. You compare these two, you put 50, and then you put 100. Does that kind of make sense? So each array has one index. Each array has one index or a pointer, whichever way you want to call it, that makes a single pass over the array. Make sense? And next time I'll show you some code so that we can go over merge sort again. But each array has just one index or one pointer, and it just goes in one direction. So in effect, you only do one pass through the arrays to merge them. Does that make sense? You only need one pass through the arrays to merge. And the idea is because to find the minimum element, you don't have to go through the arrays. All you have to do is compare the first elements. Question?
How do you get to the part where you split an array in half and both of those parts are sorted without going through the array?
So that's recursion. So that's why it blows your mind when you actually see the code. It's essentially, it happens recursively. So you assume that you made a recursive call. You actually assume that it does its job. Of course, you don't know how it's going to do its job. But in effect, basically, you can assume that. Yes, eventually it splits it down into one element blocks, fixes those, and then it merges 2 element arrays, then 4 element arrays, so on and so forth. Does this sort of kind of make sense? So hopefully you're convinced that merging 2 arrays can actually be done in one pass. So let's just try to write some code that merges 2 arrays A and B. I'm going to sort of write in pseudocode. And let's just say that, I don't know, n is equal to a dot length and m is equal to b dot length. Right? So that's n and m. So you start with what I'll call an A index. So let's just set that to 0, and a B index. We'll set that to 0. Yeah. So now I need to do a while. We'll figure out what needs to go in the while loop. And let me also define, let me just say that there is an, I'll say out index is equal to 0. Just for convenience, assume out is, well, okay, so maybe I'll do that here. So out is, array of length n plus m. Right, that's where I'm going to actually put the output. So I have to create some output array here. So I have some while condition. So what I'm going to say is while if A of A index is less than B of B index, I'm going to set out of out index equal to A of A index, and then A index plus plus. Else, I do out of out index equal to B of the B index, and then I move the B index. Plus, plus, and then over here I have to do out index plus plus, and I'm done. And I'll just return the array out. Let's forget it. Let's just ignore what's there in the while loop. If A of A index, so think of, you have the two arrays A and B. There's A, there's B. There's an index pointing here and an index pointing here. Sorry. Just going to move that out of the way. You find out which one is smaller. You assign that, and then you move that index. Does that make sense? You have to be a little careful with the while condition. And given that we have 5 minutes left, I'm not going to get into that. But yeah?
Wouldn't it just be while out index is less than equal to m plus n?
While out index is less than equal to m plus n. Yeah, yes. That's the easiest way of doing it. Or you could put a condition on in index and out index, but that's right. On A index and B index, but yeah. Well, let me just write that down then. While out index is less than n plus m. Because every time you go through this loop, you increment out index once, and you know exactly how many times it has to increment. Yes? So good, exactly. So that's why you have to be more careful over here. Yeah? Good question. So if they're equal right now, I'm just saying that I'm going to pick the B one. But you could also put less than or equal to, and it doesn't matter. So this has to be fixed. And you can fix that actually by putting something in this if block over here. So in the if condition, you check for whether A index or B index is outside the range. Right. So this has to be fixed, which I'll fix next time. But the point is you just have two indices, A index and B index, and they just sort of keep marching through the array. Make sense? Yes? Is there a faster algorithm than this? No. Why not? Wait. We still have a few minutes left. Yes? Back. Yeah. I mean, yeah, exactly. This is the best possible you can do, because in every move of the while loop, it actually finds one more element to add. So it's basically optimal. Like there's no I mean, it only goes through the arrays exactly once, which is the best that you can hope for. So this is the code to merge. And when you have the code to merge, you can basically write merge sort recursively, which we'll do next time. Yes? Ask me after class.